Okay, hi everybody. So my name's Adam Smith, as was covered there. So I am a tester by nature. I am a quality specialist. I'm a quality engineer. My focus throughout my entire career has really been on quality assurance. Part of what I do is to be a general CTO of a testing consultancy, but a few years ago we started building a product. And we started to build AI into that product. And that product used people's identities as well, as David was just talking about. And a lot of the issues around AI, QA, and particularly trustworthiness, which was a word on the slide just a minute ago, really started to come to the fore in my head. So I started getting involved in this from a number of perspectives. One was, how do we test AI? And one was, how do we build trustworthy, ethical AI? So I'm going to talk a little bit about the journey that I've been on as we go through these slides. And what I'm going to try and give you is the 10 things that quality assurance specialists need to think about when they're working with AI. Because I'm an AI skeptic. I'm not that convinced by the whole thing. I may run an AI team, but I think there's a whole load of issues out there. And I think these issues are not really very well understood. There's not really very many methods, tools, and techniques that are well understood, well known at the moment for dealing with some of these problems as well. So as well as that, as David was saying there, I work on standards development. There's a whole load of conversations going on at the moment about, so I'm going to get boring and standardsy now, about ISO 29119, ISO 2510, so standards around testing and standards around product quality, standards around things like functional safety, things like cars, and how all these standards need to change to deal with some of these big problems. And not all the answers are there yet. So just to start with, so everyone wants trustworthy AI. The number one issue with AI adoption is trustworthiness, and to a degree the technical elements that help us build more trustworthy AI. In every enterprise survey, in every survey run by governments, in every piece of legislative inquiry that's going on in the UK, in the EU, in the US, even in India, these are the main focus. This is the main focus. How do we build trustworthy AI that people want to use? So trustworthiness is obviously a quality characteristic. So trustworthiness is an element of how satisfying a product is to use, and it's an established characteristic that you measure in a software product. But it isn't normal that we have new technology and then we need new QA and testing processes, right? So when blockchain came along, we didn't go and develop a whole load of testing techniques. When big data came along, we didn't really generate new testing techniques. But AI is different, and I'm going to explain slowly how these things are important and how it's different to other technologies. I mean, one obvious example is it's not a technology, and it's not very well defined what AI is anyway. You can define it by its research goals, things like computer vision, speech technology, ability to make predictions and decisions. You can define it as the application of knowledge through computer software to have an influence on the real world. These definitions, even they aren't standardized. It isn't one thing. There's a whole bunch of technologies beneath it. There's machine learning, which we're going to talk about later, which is sometimes called sub-symbolic AI. And there's something called symbolic AI, which is the expert and rule-based systems that people worked on very heavily in the 80s, which are kind of a bit of a dated concept, but they're starting to re-emerge when they're combined with things like machine learning. So there are at least 10 specific AI quality problems. I wanted to find 10. I found exactly 10, so it should make a good blog for social media as well. So quality problem 1. So another definition of AI is it's automation without specification. So if you think about it, if you're a traditional software developer, you get requirements, you get a spec, you write some code, you're probably not applying much knowledge and context. You're implementing that specification, the tester picks up the specification and the requirements. Fine. But what if the system isn't explicitly coded? What if it's using machine learning and is learning based on data that we're throwing at it? So a machine learning model will make decisions, predictions, classifications, count things, group things, etc., based on things it's seen before. This is really crucial because if we aren't going to explicitly say what the software is supposed to do, how are we going to know whether it's right? How are we going to separate out edge cases from positive results? And this is really an Oracle problem. So those of you that are A testing specialist will know the Oracle problem is when you can't determine if a test has passed or failed, or can't determine the criteria to determine if a test has passed or failed. And pretty much, it's pretty much the biggest problem in software testing. Most of the projects that I've seen go off the rails have been suffering from huge Oracle problems. And this is equally also the reason why, just a little tangent here, you'll see a lot of people talking about test automation and AI. This is one of the reasons that AI isn't going to take testing jobs away. It's because most of the job actually involves talking to stakeholders and figuring out what they actually want. And AI is not going to be able to do that for you. So don't worry too much about that. But yeah, the root of all problems with AI and testing is primarily down to this. If we're not going to specify what we want the software to do, how will we know when it does it? So this is problem number 1. Problem number 2, and this doesn't apply in all cases, but if we don't know the answer and we're writing the system to figure out the answer, how are we going to know if it's right? So if we're building some kind of complicated mathematical system to figure out which planet can have life on Earth, that's going to be pretty hard to test, right? But one of the things that you can do is establish expert panels. So with AI, you're typically trying to replace an expert making a decision. And David mentioned it there when he was talking about people looking at photos and determining fakes. So you can actually bring experts in, and you can get them to replicate the same decisions as AI. But this leads to problems which can be called bias, but I'll come back to that later. One of the problems is, what if the experts disagree? How are you going to deal with that? It doesn't take you any further to determining if your test has passed or failed. What if the expert's not actually very good? How do you baseline that expert capability? What if the expert's actually influenced by the fact that they think the AI decided that one? So a lot of these things are done what's called double blind, where people don't know which test result is coming from reality versus the AI one, and the experts don't know the answers either. Another thing that you can do here when you're using experts is to use them at scale to try and validate a system that's processing a lot of data. But one of the things that you'll have to start to think about, which you're not used to thinking about as quality specialists, is statistical significance. Because as soon as you get into statistical systems and you're trying to test things by doing exploratory functional test cases, you're going to find some variation in results. So statistical significance is an important concept to understand for quite a number of test approaches with AI. Just go back to the experts. If you're sat in front of an expert, they can say things like, well, I'm not sure, but I think it's that one. So they just said, I'm not sure, but, right? How do you then compare that to a test result? How do you inject that uncertainty into your pass-fail criteria? So this is a problem, but most AI systems that people work on are calculating answers that people do know, so it's probably not the biggest one. Let's go on to number 3. Right, so AI systems that interact with the real world, we often talk about them as having sensors, so they can sense things that's going on around them, and actuators, so they can influence them. If you're testing something that has many real world sensors, or maybe has many inputs for small amounts of sensors, so think about a smart city with things on lampposts measuring people, how many people are going past, and trying not to count the cars as people. You've got to think quite a lot about how you test that. You've got to think about the test environment, the test data in quite a complex way. But it's not an insurmountable problem. We're kind of used to replicating data and interaction with software in test environments to a degree. But what we have is greater volume. We have greater variety. We also have other aspects of the environment that you might need to consider. So is this an AI that's making a one-shot decision, or is there a sequence of events? Is it sequential? Is this something that operates within a fixed, zoned, discrete space, or something that can wander out there? Is this something that has one AI agent in the environment, or is it something that has 2 or more? Is the agent able to observe everything that you can in that test environment? So real-world sensors are a problem, but generally AI test environments have a whole load more considerations. Even the data that the system's been trained on, the collection procedures that were used, to gather that data and train the model can kind of be considered part of the environment rather than the system itself. Does anyone know what the pesticide paradox is? Anybody? It's in ISTQB Foundation. Okay, so the pesticide paradox is the more you test a specific thing, the less bugs you'll find in that area, either because you're gradually working out the bugs, or because the developers become focused on that area, or you build automated tests that give you really good coverage in that area. But what if you're testing in your test environment and you've got something in there, a feedback loop, like reinforcement learning? So every time you do something, it influences what happens next time you do it. So I had a problem with this when I was developing, working on a chatbot, because the first thing we did, naturally, new project, let's build some automated tests so that we don't have to do them twice. The automated tests never broke. They just carried on working better and better. And my chatbot model, which was outsourced to Amazon at the time, was basically using reinforcement learning to refine the results I was getting. It was overfitting to the things I was asking in testing. And that meant the things I wasn't testing got worse. So you need to think about tests, and you need to think about optimization and how the system optimizes itself when you regression test it. Number 5. So, if this system is intended to mimic human capabilities, what are human capabilities, right? So, again, I use a chatbot example because it's easy to imagine, but let's say you had a requirement to make sure that a chatbot isn't going to upset anyone. How do you then turn that into a series of testable requirements? Well, you have to think of everything that could upset anyone. You're going to have to enumerate that. You're going to have to create a bunch of test scenarios to make sure it works the right way. That's going to be hard. And this is constantly an issue when, it's constantly an issue with AI, because a lot of the focus of AI is replicating human intellect. So if you can't define human capabilities, and if you can't define human intellect, you're going to have trouble. But it's not just the testing that's going to give you trouble, because, well, I suppose testing with users is still testing. It's not just your testing, it's when you test with users. What you're going to find is you're going to develop a significant amount of new requirements during any kind of testing. It's not so much the volume of testing that you're doing as the volume of people that are being exposed to the system that will actually drive out defects. The other problem you've got is knowing whether something's a bug or not, kind of like an Oracle problem. If the desired goal is that you replicate human capability, and everyone's different, everyone has a different perception of what human capability is, then you're going to have a constantly shifting set of requirements and test basis. A really simple example of this was a voice recognition app I worked on, where you had to say a wake word, which I think was OK Neuro, our internal app, or Neuro, I think. And then you had to say a question, and it would answer you. And one of our users said it never worked. And we couldn't work out why it never worked for her. And what she was doing, she was, because she was used to an Android phone, she prefixed every request with OK Google. And she thought that it was AI, so it should just know that and it should figure it out. But obviously, the development team disagreed, right? Because if you don't say the right wake word, the system is not even going to listen to you. And this comes down to some trade-offs, because continuously throughout the development of an AI system, you do have to make a lot of trade-offs. Coming back to a chatbot example again, I saw something on LinkedIn yesterday where someone did a chart relating the complexity of your dialogue to the perceived quality of the system. And the more you try and add functionality and parameters in to a chatbot, the less it will work. Amazon themselves, I think, recommend that you, because they do this like back-end chatbot engine you can plug into, they recommend you never try and do more than 100 things in a single chatbot. And part of this comes down to the fact that we're actually decades away from developing proper AI. What we're dealing with at the moment is narrow AI. So when you can't solve a problem like general artificial intelligence, which we can't at the moment, what you do is you break the problem down into smaller chunks. So we're building lots and lots of narrow AIs that are very good at specific things, but can't do things generally. And that's why something like a chatbot or an Amazon Alexa will struggle to scale. So I told you I'm an AI skeptic, by the way, at the start, right? And I'm only halfway through. And these are big problems, these trade-offs. And there's actually a few more. So quality problem 6 is called, in mathematical circles, the no free lunch theorem. And the theorem says that any general purpose algorithm is equivalent when its efficiency and accuracy are assessed against all possible problems. So I'll take 2 examples of this. So one is, they're both search problems. So, if you're trying to find your way out of a maze, they say the best way is to always take the first left and carry on going around the outside until you find the exit. Well, if that's true, and you built an algorithm that did that, it might be very efficient, but it's probably going to be efficient on mazes where the exit is found first if you follow it around to the left. If you flip the maze round, that algorithm that you developed that's great at mazes with an exit somewhere on the left is going to be terrible if the maze is on the right. Another example is if you built an artificial agent that's job was to go to a planet, right, and map out the topography of the planet. And you're going to get very different performance if you start it at the bottom of the hill versus the top of the hill, okay? If you then took it to another planet that had a different kind of geology, a different kind of earth structure that we hadn't seen before, it would be much less efficient. So the essence of this theorem is that it is not possible to come up with algorithms that are efficient across all possible problems. And that comes back to the problem we have with artificial general intelligence. And what we haven't been able to do is train artificial intelligence to learn in one context and apply it effectively in a different context. And this is very, very closely linked to the next problem. And this is the number one problem. As part of trustworthiness, this is the number one problem. So what is bias? So bias can be defined in a lot of different ways. So bias can be defined as in statistical terms. So in statistical terms, it is, in machine learning, it's the impact to the effectiveness of the model by the difference between the data that you've trained it on and the data you're using it on. So it is, in effect, a mathematical way of defining the representativeness of data. But it can also be a process bias. So what if I'm only what if I'm labeling my data and I have some inbuilt prejudice, laziness, some human aspect that changes the way I do things? It can also be a psychological cognitive effect, so psychological bias. Maybe I'm biased towards people who are in the same group as me, biased away from people who are perceived to be in a different group of as me. And there's a few more going on. There's quite a lot of definitions of it. But coming back to a machine learning model, it's really about the data and how representative the data you use to train your model is when it comes to real world. One of the reasons this is one of the biggest problems is going back to the previous slide, the no free lunch theorem. Bias is a trade-off with variance. So if bias is how representative the data is of production, variance can be described as the sensitivity of the model to different types of data. And the more you optimize for a specific scenario, the less you work well in a general scenario. This is a recurring theme throughout AI. There's a trade-off between working in a specific environment and working generally. Give you an example, it's kind of real. So one of the big machine learning data sets that people play with, especially when they're doing data science training, is the Titanic data set. Now, the Titanic data set, when Titanic sunk, there's a lot of correlations you can see between people's social class, gender, age, and whether they survived. And if you took the Titanic data set and put it through some Python and stuff like that, you'd see that the biggest correlation is gender, because people let the women and children off first, right? So gender was the biggest correlation to survival. So if I train a machine learning model based on the Titanic, a couple of years later, there was a ship called the Lusitania, I think, that sank. My history is not very good around this. I've only been looking at this from a data perspective. The Lusitania sank, and people had learned. They didn't send the women and children off first. So the correlations are completely different. So the correlations are actually more based on, I think, age in the Lusitania. So if you take data that's happened in the past around the Titanic and try and use it to predict who's going to survive on the Lusitania, you're going to get it all wrong. And this is really the essence of bias and how it applies in machine learning.
It got torpedoed.
Did it? That wasn't an input to the model. So yeah, so bias in a statistical concept is really about data, but how you, as I said before, how you collect data, how you label data, how you integration test your system can also result in bias in a slightly different way, in a more societal way. So let's say you have an ETL bug in your data integration feeding into your AI model. You know, your data scientists probably aren't going to look for that when they're testing because they're not testing with an integrated environment. But you can end up dropping data items and records that actually result in a model that gives very different results to the one that you've trained and the data scientists have worked on and proved works in the lab. So there's a whole load of issues around this. This is the number one issue. I put it as number 7 because I wanted to work up to it, but this is the number one issue that's out there to be solved. Number 8, you've trained your model, you tested it, it all worked, you put it in prod. But then reality changes around you, right? The relationships between the inputs and outputs of your model, the input domain, the output domain, the correlations can change over time. People's expectations can change about what they expect to see. This also is tightly related to, probably doesn't come across on the slide, but regression risk. You know, when you're typically changing a line of code, you're generally doing a focused retest. You kind of understand what's changed. Typically, when you rebuild a model with a different data set, you're rebuilding everything from scratch. You're back to square one in terms of testing. So you can't test specifically for the inputs and outputs changing over time, but you can think about it and build in things like regular, repeatable regression test cycles. Number 9, ethics and fairness. So I'm going to give lovely offices at Onfido. I'm going to give an example from a competitor. So Experian. Experian built a system, and they used it for assessing fraud, which is what they do in financial services. But this was in UCAS, so you know where you apply for a university place in the UK, you go into like a clearing system through something called UCAS, right? So they've got all these models they've trained, who knows on what, and they used it to reject university applications because they were a fraud risk. And it turns out that you were 60-something% more likely to be flagged as fraudulent risk based on what country you came from. So they've put bias in their model, inadvertently, presumably, and they've taken a model and they've used it for a slightly different use case. Now, there's so many examples of this used in the criminal justice system where recommendations are being made to judges about whether they should let people out on the streets and whether they're going to commit violent crimes. Police forces all over the UK are using systems like this to predict where crimes will happen and try and deploy police forces. It's used extensively in social care as well, in terms of identifying things like potential abuse cases in childcare. It's used, I could go on forever. There are so many implementations of machine learning, and it is so unregulated. When you use it with personal data, there are masses of risks around ethics and fairness. You've probably heard the trolley problem with self-driving cars, where what happens if the self-driving car is going down the street and there's a woman pushing a baby, and it has to swerve to avoid that, but it might kill the owner. Yeah, that's quite a long way away compared to this issue of machine learning right now and personal data and how it can actually impact people. It's not really a testing problem to make sure that things are ethical, but it is something that you can ask, right? One of the reasons I think it's so important for testers and quality specialists to be thinking about AI is because there's so much critical thinking that needs to be done about its actual quality. Because it is statistical, it's probabilistic, it's complicated, and it doesn't return consistent results. Here's another one. What if we actually do trust it too much? So I did a testing review of a project where they were using machine learning to replace what data entry clerks were doing. And when I got there, they were in their UAT and they were going, yeah, it's great. You know, we can get rid of 300 people. We've got all these people sat here typing stuff in. Now we're using machine learning, and they just check it and press OK. I'm like, great. Have you looked at the results in the database? And they're like, no, we've just been measuring how much time it takes to do it. When we actually looked at the results, there was a massive drop-off in quality because of something called automation bias. When people believe and trust in a machine, they start accepting what it says automatically. Another example of this is the Uber semi-self-driving car where the woman was texting and not paying attention to the road. That's a classic example, right, of where a human in the loop trusts the AI too much. This is one that has a very clear testing impact. So they're my 10 problems. ISO 2510 which is my favorite go-to thing for whenever I'm doing a testing strategy, because it lists all the stuff that software should do. But it doesn't list everything that we expect AI to do these days. We expect AI to be able to learn, and we expect AI to be able to generalize. We also expect it to be trustworthy. These are kind of new things in the quality world that we need to work on and develop test approaches, test strategies, and testing techniques. So one of the things I've been working on is a certification with A4Q, which is AI Certified Tester. And it's not launched yet, but some of the things that it's covering are some of the things I talked about today. So I thought I'd kind of put the contents up there, give you an idea about what you might want to look into if you're faced with an AI testing challenge. The first is the background to AI. So what are the different types of AI? What are the key algorithms? How do technical approaches vary with different algorithms? I've talked you through a lot of the limitations today. There's a lot more detail to these. I've talked a little bit about bias and variance and the no free lunch theorem, drift, adversarial actors. So that's when people start trying to mess with your AI. So Microsoft's Tay bot, I don't know if you remember that on Twitter, that within 24 hours was saying terrible things about, I think it was George Bush at the time, or was it President Obama? I can't remember. It would have been Obama, thinking about the timeline. Ethical considerations. What are the things that you may risk by using personal data alongside AI? Perception of intelligence. How do you crack that problem of a user saying, I want it to be like a human? Expert systems. So these are non-machine learning systems, ones that use explicit rules and use deduction and inference to come to conclusions. These have a whole set of issues as well, probably less than machine learning-based systems. How to critically assess product and vendor claims is key, right? You usually can't download a free trial of something using AI and machine learning and prove it out on your own. Usually people want to keep it to themselves. Vendor claims are often pretty amazing in the AI space, as I'm sure you're familiar with from the press. And this applies as well in test automation. Okay? All these problems I just talked about, if you're using AI-based test automation, those problems still apply. You're still scaling, and you've still got the generalizability problem. How to specify probabilistic acceptance criteria. Where you're dealing with probabilistic systems like the weather, which you can't perfectly predict how they're going to behave, how can you change the way that you specify acceptance criteria to cater for that? Around functional testing, there's a number of different areas that are specific to AI. So model training and testing, which is what data scientists do. It's pretty important to understand how that's different to unit testing and how that fits in with the rest of your testing strategy. Metamorphic testing is a specific testing technique that is based on using prior test results in order to determine whether the next test passed. So this is typically used where you have an oracle problem and you can't determine the right results from the system without actually using it. And a really simple example of this is there's this complicated algorithm determining, say, supermarket prices, right? And we know that the algorithm is there to make sure prices go up as stocks go down. Maybe the algorithm's too complicated for me to figure out exact acceptance criteria, but what I can tell is if I buy one bottle of wine and it's a tenner, and I go back and buy another bottle of wine, it should be greater than a tenner. Yeah? that's a very simplistic example, but metamorphic testing is based on using prior test results to determine your next test result. A/B testing, heavily used in marketing and things like that, but is also very, very useful in testing probabilistic systems. Expert panels, so it talks about some of the problems with that and how using experts to assess whether an AI has done the right thing is a good thing, but also has problems. External validity, so this isn't so much a testing technique as the concept of using data other than from the input domain of your algorithm. So going back to ethical stuff, you might use census data. So Amazon had an example, Amazon Staples had an example where they came up with a pricing algorithm for their website that was designed to price down on things if the user was near a competitor store. And this completely backfired because someone took all their prices and did some tests and then compared it to census data and said, you're putting your prices up for people of a lower socioeconomic class. So they had to roll that one back. Around metrics, statistical significance, I mentioned a little bit earlier. That's quite important. Confusion matrices, I won't go into what they are, but these are ways of laying out effectively test results to show things like false positives, false negatives, true positives, and true negatives differently in a matrix. Because these things get too complicated to just represent in a pass, fail, or even a single accuracy statistic. And finally, learning how you apply traditional test levels to an AI system, how to build a test strategy. So these are the topics that I think people need to learn if they're starting to manage AI testing. And that's it.